The resulting set of vectors is then projected onto the eigenvectors of the covariance matrix, and the resulting coefficients form the observation vectors. The system is used both for face detection and recognition by the authors. For face detection, the system is first trained with a set of frontal faces of different people taken under different illumination conditions, in order to build a face model. Then, given a test image, face detection begins by scanning the image with horizontally and vertically overlapping rectangular windows, extracting the observation vectors and computing the probability of data inside each window given the face model, using the Viterbi algorithm. The windows that have face model likelihood higher than a threshold are selected as possible face locations. The face detection system was tested on MIT database with 48 images of 16 people with background and with different illuminations and head orientations. Manually segmented faces from 9 images were used for training and the remaining images for testing, with a face detection rate of 90%. For face recognition, this system was applied to the ORL database containing 400 images of 40 individuals, 10 images per individual, at a resolution of 92 x 112 pixels, with small variations in facial expressions, pose, hairstyle and eyewear. The system was trained with half of the database and tested with the other half. The accuracy of the system presented in this paper is increased slightly over earlier work to 86%, while the recognition time decreases due to use of the KLT features. Following on the work of Kaur and Desai wrote a series of 3 papers using the 1DM for face recognition problems. In a first paper, these authors present a face recognition system based on 1DM coupled with 2D DCT coefficients using a different approach for feature extraction than that employed by. The extracted features are obtained by sliding square windows in a raster scan fashion over the face image, from left to right and with a predefined overlap. At every position of the window over the image, called subimage, 2D DCT are computed, and only the first few DCT coefficients are retained by scanning the subimage in a zigzag fashion. The zigzag scan DCT coefficients form an observation vector. The sliding procedure and the zigzag scanning are illustrated in A. Raster scan of face image with sliding window. B. Construction of 1D observation vector from zigzag scanning of the sliding window. The performance of this system is tested using the ORL database. Half of the images were used in the training phase and the other half for testing, 5 faces for training and the remaining 5 for testing. Sampling windows of 8x8 and 16x16 were used with 50% and 75% overlaps, and 10, 15 and 21 DCT coefficients were extracted. The number of states in the home was fixed at 5 as per the earlier work of. The recognition rates vary from 74.5% for a 16x16 window, with a 50% overlap and 21 DCT coefficients to 99.5% for 16x16 window, 75% overlap and 10 DCT coefficients. In a second paper, these authors further refined their research contribution. To evaluate the recognition performances of the system, 2 new experiments are performed. In a first experiment, the proposed method is tested with different numbers of training and testing faces per subject. The tests were performed on the ORL database, and the number of training faces was increased from 1 to 6, while the remaining faces were used in the testing phase. A sampling window of 16x16 with 75% overlap was used with 10 DCT coefficients, as these had provided optimal recognition rates in their earlier work. The recognition rates achieved are from 78.33% for a single training image and 9 testing images up to 99.5%, which is the rate obtained when 5 or 6 training images and 5 or 4 testing images are used. It is worth noting that the ORL database comprises frontal face images in uniform lighting conditions, and that recognition rates close to 100% are often achieved when using such datasets. In a second experiment, the system was tested while increasing the number of states in the home. Again, the ORL database is used, with 5 images for training and 5 for testing. The recognition rates vary as follows: 92% for a 2-states home, increasing to 99.5% for a 5-states home, and stabilizing around 97% to 98% when using up to 17 states. The system was also tested with the SPAN database. http://www.kyle.e.ftb.earnit.in/user/spawn_data_base/2d_space containing 249 persons, each with 7 pictures, with variations in pose. 3 pictures were used for training and the remaining 4 for testing, and the recognition rate achieved was 98.75%. http://www.kyle.e.ftb.earnit.in/user/spawn_data_base/2d_signals/face/faces. A third paper describes the same 1D with DCT features, with a variation in the training phase. In this paper, first a mean image is constructed from all the training images, and then each training image is subtracted from the mean image to obtain a mean subtracted image. The observation vectors are extracted from these mean subtracted images using the same window sliding method. The observation vector sequences are then clustered using the k-means technique, and thus an initial state segmentation is obtained. Subsequently, the conventional training steps are followed. In the recognition phase, each test image is first subtracted from the mean image obtained during the training phase and recognition is performed on the resulting mean subtracted image. The experiments for face recognition were performed on the same 2 databases, ORL and SPAWN. For ORL database 5 pictures were used for training and the remaining 5 for testing, and the recognition rate obtained is 100%, compared to 88% when the eigenfaces method is used. For SPAWN database 3 pictures were used for training and the remaining 4 for testing, the obtained recognition rate was 90%, compared again with the eigenfaces method where a 77% recognition rate was achieved. For the ORL database different resolutions were also tested, the highest recognition rate, 100% being obtained for 96 times 112. Also, new subject rejection for authentication applications was tested on the ORL database. The database was segmented into 2 sets, 20 subjects corresponding to an authorized subject class, 5 pictures used in training phase and the rest in the testing phase. The remaining 20 subjects are assigned to an unauthorized class, all 10 pictures are used in the testing phase. For each authorized subject a HUM model is built. Also a separate common HUM model is built using all mean subtracted training images off all the authorized subjects. For each test phase, if the probability of the common HUM is the highest, the input face image is rejected as unauthorized, otherwise the input face image is treated as authorized. The results are 100% rejection of any new subjects and 17% rejection of known subjects, false negatives. As proved by, the number of states used in a 1D HUM can have a strong influence on recognition rates. The problem of the optimal selection of the structure for an HUM is considered in. The first part of this paper presents a method of improving the determination of the optimal number of states for an HUM. These authors then proceed to prove the equivalence between I, a 1D HUM whose observation vectors are modeled with multiple Gaussians per state, and 2, a 1D HUM with 1 Gaussian per state but employing a larger number of states. According to the authors, there are several possible methods for solving the first problem, for example cross-validation, Bayesian inference criterion, BIC, minimum description length, MDL. These are based on training models with different structures and then choosing the one that optimizes a certain selection criterion. However, these methods involve a considerable computational burden plus they are sensitive to the local greedy behavior of the HUM training algorithm, i.e. the successful training of the model is influenced by the initial estimates selected. The approach proposed by addresses both the computational burden of model selection, and the initialization phase. The key idea is the use of a decreasing learning strategy, starting each training session from a nearly good situation derived from the previous training session by pruning the least probable state. More specifically, the authors proposed starting the model training with a large number of states. They next run the estimation algorithm and, on convergence, evaluate the model selection criterion. The least probable state is then pruned, and the resulting configuration of the model with one less state is used as a starting point for the next sequence of iterations. In this way, each training session is started from a nearly good estimate. The key observation supporting this approach is that, when the number of states is extremely large, the dependency of the model behavior on the initial estimates is much weaker. An additional benefit is that using nearly good initializations drastically reduces the number of iterations required by the learning algorithm at each step in this process. Thus the number of model states can be rapidly reduced at low computational cost.